Hi, everybody. My name is Smriti, and I hope you are able to see my screen. I'm having some trouble with the sharing today. I don't know why. So I work at Dell as an applied researcher, and we are also working on a hybrid quantum classical solution. So my team primarily is part of a research office, which we call as Office of the CTO. We are a team of senior technologists, distinguished engineers, data scientists, research scientists, hardware and software engineers, and architects. We conduct research and we build proof of concepts that influence the technical strategy of Dell's. And this research office houses quantum computing, AI-driven enterprise, security like post-quantum cryptography and zero trust architecture, Apex as a service, and immersive enterprises, robotics, all sorts of emerging and deep tech. So my team is right now focused on hybrid quantum classical computing, and we believe that no workload runs purely on quantum hardware today. So the value is in like the seamless orchestration across classical HPC and AI accelerators, quantum backends, basically a heterogeneous compute fabric. So the one of our initiatives is infrastructure, where we develop hardware and software blueprints for hybrid quantum classical computing. This also includes incorporating accelerators like accelerator interconnects like NVQ-Link. And yeah, this was recently we verified that latency of 4 microsecond with one of the Dell servers. And yeah, so those are some of the work that we do in this space. And we have our management and orchestration initiative, where we are working on intelligent orchestration and resource management service. It's basically our tool, and I will be talking about that today. The third one is use case performance analytics, which is basically focused on customer, like guiding customer through emerging quantum opportunities and where we can apply quantum advantage, economic viability, those sorts of things. Then we have quantum and AI. We see quantum applied for AI and AI being applied for quantum in this research initiative. And we are basically exploring machine learning side of things in here with Dell and its customers. And then we have error handling, where we look at some of the quantum error mitigation, correction, suppression, all those three spaces. And we are trying to see how research on classical computation side can influence this. Then we have quantum on classical, which is particularly for evaluating dequantized algorithms, quantum inspired methods, and how classical plays a role there. So what we believe is that quantum doesn't work without classical infrastructure, and that is the main, I think that is why openQSE also kind of got found upon on this basis. And we believe that when you send an input through HPC side, you are basically utilizing the classical compute, and on the quantum side you have the quantum compute, and we can bridge this together by utilizing the best of both worlds. So this is kind of our architecture, where we are trying to apply or trying to utilize the Dell's infrastructure. So once you send an input, there you can do pre-processing at the HPC side, and then this will happen in the application space with a latency of around milliseconds, and you can utilize Dell server storage and networking for that. Then we can send that input it gets processed towards the real-time host accelerated server, which includes your like real-time host to field the physical QPU requests and serve the AI acceleration needs. This includes FPGA, again, GPUs and stuff like that. Dell provides that again, and we can establish microsecond latencies with the quantum controller in this communication. And that can also be further reduced with physical QPU to about like nanoseconds latencies. And now the communication from quantum environment travels back through real-time force accelerated servers, which are again sent back to the HPC side to the accelerated servers or HPC. Um, basically using Dell infrastructure, and we also can run virtual QPUs on these Dell servers boxes, and yeah. So the capabilities of QPUs scale up. We would need, as they scale up, we would need like more classical infrastructure to support it, and then the accelerated server functions as like your real-time host to, like I said, to field the physical QPU requests, and both of them working together kind of makes everything happen quickly in the real world. So right now we don't have like a clear winner in the physical QPU environment, so we provide multi-vendor support with location independence. So yep. And so there is one more thing in this architecture that, as I was saying, we can do the pre-processing on the HPC side. We can do co-processing with that real-time host acceleration. So that's where your online calibration or like real-time calibration and quantum error correction can come into the picture. And then the post-processing can also happen on the HPC side. So yeah, this is why I think we can best utilize both the worlds, and then there wouldn't be any compute wastage as such. So this is our quantum intelligent orchestrator. This is like an old version of it, which is where we started like what 6 to 7 years ago. We did I think a POC with IonQ, and we were able to establish that we can have hybrid quantum classical computing space working as a thing, which wasn't known to a lot of people back then. So you can see here that initially this is like an end-to-end actually managed classical and quantum hybrid computing system, and the users can send their jobs via Jupyter Hub. So earlier we only used to support Python notebooks, and which had the support for different types of Qiskit, Cirq, Penny QDAQ, those kind of frameworks, and we initially connected it over cloud through to our QP provider, and we used Kubernetes at that time because of its production ready and different other capabilities. Yes, so these scalable solutions for various application needs can be supported by Dell's infrastructure, and this was like our proof that we are enterprise ready from day one. So now today we are okay. I had animation as well. Well, I forgot about that. So now, today we are looking at this architecture, which may be which has changed like a lot from where we were 7 years ago. But the thing is that overarching idea is still the same, that we are trying to bridge the HPC and the quantum all together through our control layer. So QIO, like our quantum intelligent orchestrator, basically is a vendor agnostic machine learning driven orchestration engine developed by our research team. And you can think of this as like an intelligent brain that sits between your classical HPC and the quantum hardware, which automatically coordinates, optimizes, and routes your workloads across both the worlds. So we have this one control plane, which and you can use any quantum hardware with this. So let's look at one layer at a time. So the users can actually send the problem in the form of a simple circuit or in the form of different jobs, which can be tied together using singularity images. So Yeah, so yeah, our client API is capable of handling simple circuits or demystifying that image which you have created in Singularity, and then we provide access to each of the users using their own passwords and tokens. And so at the top, the user kind of submits the problem through the client API, and those problems land into the QIO master, which houses our orchestration engine. So the intelligent, that is like our intelligent core here. And this engine handles circuit cutting, knitting, which is basically breaking the large quantum circuits into smaller pieces that today's limited quantum hardware can actually execute. And then through knitting, you are basically stitching the results back together. We have our machine learning driven runtime prediction, which basically predicts how long a job will take on different hardware targets, and resource optimization, which is also machine learning driven, where we intelligently allocate compute across available QPUs and classical resources. Then we have error mitigation. So in this engine, we have incorporated techniques like zero noise extrapolation that improve the accuracy of noisy quantum results without requiring better hardware. This is like and then we have, yeah, so yeah, by building on Slurm here, like what you are seeing in the job manager, um, we ensure that quantum workloads are treated as first-class jobs alongside classical HPC workloads. And this was one of the reasons why we chose to move from Kubernetes to Slurm, and also because of its simplicity. Yeah, so the job manager, you are also seeing like on the right-hand side that there is a quantum task and classical task. So basically our orchestration engine divides your job into quantum and classical tasks, and then it orchestrates using Slurm. So the job manager dispatches work to the QIO workers, which can be one or multiple, and we run, which are basically run using Slurm daemons. And we handle both classical job execution and quantum job execution through our modular framework, QPU driver frameworks. So like what you're seeing here on the left is a QPU A driver, which would work for one vendor. And then similarly, we have other drivers which would work for different other vendors. And we also have, like, for example, if you have Qiskit, so if you are doing emulation or like the virtual QPU, support can be provided through one driver, and the actual API or actual device support can be provided using another driver. And these are very agnostic, such that each driver is abstracting the vendor-specific complexity of a particular quantum platform. And we have like basically the backend transpilation and all the API information behind a consistent interface. So yeah, moving on to the next layer, we have a control layer. So this includes the QPU control infrastructure. Um, So this includes control boxes, instruments, calibration, low-level IR conversion. Today, this layer is like managed by our partner ecosystem. And in our forward, like in futuristic architecture, Dell envisions a co-located QIO gateway that would place this real-time control layer directly alongside a quantum processor within an HPC environment. So but yeah, this is an architectural target we are building towards, and not like a current state capacity. You are seeing the NVQ-Link framework here, which is a unified interface bridging like supercomputers, logical QPUs, and physical QP layers under a standardized abstraction. And yeah, we verified that latency using Dell servers. And this is in the microsecond deterministic time space. Yeah, so this is the last layer, the qubit layer, which has multiple QPUs vendors supported. Like I was saying, QPU A driver can have silicon spin or cryo CMOS support, and we could have superconducting support, and all would be housing in the same QIO orchestration software on the HPC side of things. And basically, Dell owns this intelligence, and we partner. Our partners own the quantum hardware, and the interface between them is clean, modular, and extensible, which we are trying to develop towards, or which is also called our QIO. So these are some of the prime functionalities of the orchestrator. This is mostly repeating what I mentioned earlier, and we are basically interested in this because in most quantum computing frameworks today, error mitigation, post-processing, and circuit preparation happen sequentially, one step after the another, but QIO leverages Dell's HPC orchestration and our proprietary machine learning models to run these classical pieces in parallel. This reduces the time to result quite significantly, and we have seen established this on a few of the use cases. So we also support some synergy with Dell AI Factory. Basically, when enterprises want to run HPC simulations, the massive GPU clusters configured in the Dell AI Factory serves as a powerful classical backbone that orchestrates and processes heavy data workloads. So this is where the Dell AI Factory comes into picture. And you might notice that there are two extra bubbles here. One is the transpilation and one is the queuing optimization. So the transpilation is something that we are doing in-house in QIO, and also the optimization, which happens in our resource estimation pipeline. So this is an example on our QIO, of our QIO steps, like how it would look like if we are doing circuit cutting. So imagine you have like your user input has about 33 qubit circuit, for example, and our service level objective or SLAs say that we have to do a fastest execution and we cannot increase the cost of $1,000 or so. So we would cut that into, I would say, 4 subcircuits, and such that each circuit can be run on a machine with 28 qubits max. And then we would do some runtime prediction where we would run all of these subcircuits on 4 different, there are 4 subcircuits, so 4 different environments. And so, for example, if one is being recommended for Intel, other one is being recommended on NVIDIA's GPU, leveraging NVIDIA's GPU, it is being run in 3 seconds. So these are some of the execution time and memory consumption prediction, which we would do in real time, and also leverage that for our estimation pipeline. So the resource optimization then happens using that runtime prediction of each subcircuit for each environment. And so the fastest execution time, while not exceeding the user-defined target, we would categorize each of the devices which will be used, or like each of these resources which will be used to run that 33 qubit circuit. And this is like one scenario of how we are doing in parallel execution of a use case of the workload that the user has given to us. And similarly, we have done this with credit risk portfolio analysis while we were comparing it with the Monte Carlo simulations. And we were able to actually see a lot of speed up when we tried to execute for around 10 assets, which would help us emulate around 32 qubits. Yeah. Similarly, we have done for different other use cases like MaxCut and GHZ state simulation and different stuff. And so these are some of the deployments that we have done with our partners. In SC25 last year, we represented, I'll be showing you a demo of what we actually did with QERA. And so this was like our first POC to connect with our HPC mini cluster with QPU side by side. And this is like a demo of the environment, which served as a basis for our presentation there. And then we are doing some exploration with University of Washington. We are also looking at Arizona State University, some of the research there. And then we are supporting Dirac, Dirac's lab in Sydney, and the integration is happening with QIO. Then, like just today, it was Able One was integrated with QIO, and this was happening in Cork, Ireland. And yeah, it was like a successful thing that we have been celebrating in the team since morning. I'm gonna play this demo and I'll walk you through what actually it looks like. So what you're seeing on the left is basically the Jupyter notebook, which we use to kind of run the workloads from the user. And on the right, we have our visualization dashboard, which is using Grafana. Yeah, so basically in this scenario, the user has submitted a job. Actually, they're first plotting it. This is an unoptimized solution which is running GHC standards. And this is a simple GHC state preparation that we are doing here. And it uses it is using 7 qubits, okay. So this is where the token and the host information goes into the picture, and it is specific to per user. And then the backend, what you're seeing here, we have this capability of like QIO has this capability of selecting which is the best backend for this workload. Mhm. And we are running the task, and it will, like on the right hand side, you can see it's the partition is called classical first, and then it gets distributed into the quantum classic partition as it starts using that, and then we will see the number of different tasks which are being split and calculated how much time they are taking or how much memory they are consuming. Pause it. We had around 2 nodes in that mini cluster. And so one of them is using, yeah, about 0.6 GBs of RAM. It's also, hmm. So once your job actually completes, you would get that message in the when you will kind of print that, and you would see that it has completed, and you will get what the bit string look like, the plot is the histogram. And this was a unoptimized solution. And what I mean by optimized solution is that now we had this capability, or like for specifically for this scenario with QERA, we had a parallel gate execution, which we called as optimized. And this is what we were running for the second scenario. And we were able to, you can actually mention the number of shards. You can mention if you want to use the transpiler, like our own transpiler, or you can like bring your own transpiler if you have like on the quantum side. And then if you want to use cutting for a specific workload, then you can toggle that option on. And similarly, it will show you the other jobs and how it is being split into classical and quantum tasks. So yeah, it takes a little bit of a time. And yeah, after it was completed, we were able to get the result. It says completed. I mean, if you would actually print it before, it will also tell you that it was running or in processing or if the job is broken. So yeah. And this is like the final histogram which we got after everything was executing perfectly and it was using GHC in optimized state, which was using qubit shuttling and parallelized gates. So yep, that's about the presentation. Any questions?
Thanks, Smriti. I do have some, but I'll open it up to the group if there's any questions. Go ahead, Gary. We can't hear you if you're talking.
Yeah, okay. Yeah, so could you talk a little bit about the resource estimation? Is that estimation just, for the simulation or for the classical part, or do you have some model and estimation on what it would take on the different QP of a different modality?
Yeah, so it's a proprietary thing, so I cannot discuss much on that, but
Mhm.
it's yeah, it's using machine learning models is all I can actually say.
And is it just for classical or for computer both? I mean, or if you can say, I'm just
Um, yeah, we considered telemetry, but yeah, I cannot really. I'm
okay,
not
that's
at
fine.
liberty to say. Yeah.
Okay, all right.
Laura?
Hello, thank you for the presentation. That was great. And sorry, I had a little bit of a network lag, so you probably covered this, and it's a redundant question, but I wanted to check anyway. I was just curious about like the upward feedback path from the quantum systems into the orchestration. Um, so how is the device state, the runtime health, how does that influence the higher level scheduling and the workflow decisions? Because you were mentioning about location independent, that implies some, some other, some feedback from the system over the network to the HPC. Kind of what does that look like? That part I missed.
Yeah, so the feedback that goes back into the real-time accelerated server, is that the one you were pointing towards?
Yeah, so basically like the runtime, the state sorry, the device state, the runtime health, how that's getting back up to the higher level scheduling and workflow decisions.
Right. So okay, yeah, we are like in this scenario, we are talking about communicating what we are getting from the API, like for this neutral atom example, if we would consider.
Hmm.
Yeah, there were like API responses which we were triggering, and we were getting I mean, the request was sent via API, and the responses that we were getting had some of those information. So we were kind of trying to leverage that for telemetry, but yeah, yeah, that was like using the APIs. And
Okay.
when you consider about the location specific thing, I meant for vendor agnostic sites. And
Okay.
that is like, yeah, like the on-prem solution that we are trying to sell here.
Okay.
So yeah, I was talking that we would consider on-prem solutions, and that would be at the vendor site.
Mm. Okay.
Um, Following up on that question, like the APIs that you guys are using to talk to the hardware, is it something the proprietary that you developed?
So for neutral atom, it was provided by QRF. So we were leveraging that, and we have like our drivers, which are modular, and they kind of abstract everything, and we try to use the API, like try to abstract that API information inside those drivers.
Okay, so you developed your own abstraction layer. So if you have
Yeah,
multiple QPUs, then you develop your own abstraction layer that abstracts away the
yeah,
details of
for
each of the hardware.
each of the vendors,
Okay.
yes.
Um, can you talk a little bit about which QPUs you mentioned, Q era, and then your diagram, you had the control and you had the NVQ link, and you said
Mhm.
that you measured the NVQ link to be 4 microseconds. I'm just wondering how you did that measurement. Was that like you have some sort of a control box on-prem that you guys are using, or how did you like do that measurement? If you can talk
Yeah,
about it.
so yeah, this one that you are seeing is, yeah, this wasn't done with UIO, it was done independently of UIO. And the latency that we verified, it was done using Dell's server. We connected it through to an FPG, and then we ran the error decoder algorithm that is mentioned in the NVQ paper.
Okay, so the FPGA is your own FPGA and the
Yeah.
Dell box is your own Dell box and you just connected
Yes.
it via the NVQ-Link protocol.
Yep.
Okay. I have a few more questions, but anybody else wants to jump in? All right, I'll keep going. Um, okay, so I missed this part when you talked about, yeah, in this diagram, you had the quantum and the classical tasks. Are those, you said they're fed in through Singularity? I'm not very familiar with Singularity. Is it
Mhm.
like a way to describe an application?
Yeah, so Singularity kind of gives you a way to package a lot of your workloads, like package, I would say, if you write a def file in Python, you can actually package all your code together and it will create an image. And then you can read that image with Singularity, and then you can, it's like kind of pickling, and you
Okay.
can unpickle it and, yeah, use all of that information in your code. So we are trying to wrap all of our content that the user is sending. If they want to send like bigger workloads for large scale problems, so we can use Singularity and we can containerize some of our environments as well.
So then your client API, when at the top of your diagram there, when you say problem
Mhm.
submission client API, the
Mhm.
user actually submits that Singularity image and then you guys parse it, or is that something built inside the QIO master?
So yeah, user can do both. If you know
Oh,
how to use Singularity, we can tell you how we can accept the data as, and then we can store it into our database. And then QIO can read it from the database. Or if you want to directly send a circuit in the form of a job, like a normal circuit also would work. And if you want to directly send a circuit, we would read that and we would store it into our database, and then we can have it, we can give it to the QIO. It will do the orchestration, workload management, and the entire process.
okay. And I'm guessing you still support, like in the previous diagram, I think the earlier one you had SDK, multiple different types of SDK like Qiskit. You support that, you wrote like backends for them to talk over the client API that you have there?
Mm, this one or
Yeah, yeah, like there is some sort of application, the problem submission is like somebody wrote a Qiskit application and that he wants a
oh
Qiskit
right.
script and he wants to submit it to your workload. Exactly, is that you so you have some sort of backend for your for Qiskit and Circ and QQ that talks to through your client API?
Yeah, so if you're yeah, whatever circuit you are submitting to us, we would actually translate that using this layer into Qiskit, Penny or QQ, or yeah, Surf, or even more. So it depends on what kind of hardware we are interacting with, and we can change it from one to the another. But yeah, it also depends on the intermediate representation part, which we are working upon right now.
Peter, go
ahead. Yeah, thanks very much for the nice talk. And sorry if you already answered this, but I had a question about scheduling. So let's say if you had hybrid jobs that consist of sort of both quantum tasks and classical tasks.
Mm-hmm.
Is the scheduling effectively done by Slurm of both? Did I get that right? Or is there something else that's sort of doing some extra scheduling on the quantum side?
So we are dividing your original workload into quantum and classical tasks. Like take, for example, error mitigation. You would have folding of the circuits, right? The folding of the circuit happens classically. So that falls into the classical bucket and we send it to our regular resources like CPU, GPU. And the running of the circuit, or like when the noise amplification happens and you have to run it on a noisy backend, that part would go to the quantum. And the the extrapolation part, that would again happen on the classical side. So all that split is happening inside QIO.
I see. But so if you imagine you had a job that consisted of like some many quantum class, like maybe some variational type algorithm or something, like would the scheduling basically be done for the whole thing in one go? In other words, like the whole job would be scheduled and the resources would be allocated at that time, or would something else happen? Would you split that up and sort of schedule, allocate resources only whenever required?
Part of it is proprietary, but yeah, we are using our machine learning resource optimization model, which kind of helps us in decide which resources should be used and how much resources should be used for scheduling these tasks. And so, yeah, I think I kind of explained that in this example.
Okay, thank you.
I actually have a question. Sorry, does somebody want to say something? Go ahead, Yuri.
Yeah, just to follow up on this, right? So the decision to cut the circuit is done a priori, or is it part of is it with some feedback from backend capability? Speaking at a high level, or it was in the demo, probably was by hand, but how do you envision, or how do we envision sort of this happening? Because how do you cut the circuit is dependent on what the backends can do and what the capability of the non-QPU portions are, right?
Yeah, that's dependent on how we have trained the model. So yeah, it has seen some of the data that we have trained it upon, and based off of that, it makes certain decisions. But yeah, we also kind of yeah, when we are sending the circuit, we provide like it estimates how much resources would be required for each of these subcircuits, for example, and we would allocate those resources. And then so basically that's how it is working, if it makes sense.
Yeah, I'm trying to speak sort of conceptually, right? So something knows of the complexity of the circuit, right? It is dependent on, to some extent, with to the backend capability. By ignoring that, there is some aspect of learning or reinforcement from previous like circuits that decide how to cut it, and then how to estimate the thing. And I'm just trying to understand a little bit what you said. Is it kind of how you envision that going forward, or how it may work hypothetically?
Yeah, I mean, in an ideal scenario, you can take that into consideration. It's about training your machine learning model, how much you want to, what features you want to train it with. So I guess conceptually, if you give it certain circuits and you are getting some performance for each of those circuits, then you would kind of try to prioritize that based off of what the service level objective is, right? Like it would have a feedback mechanism if it is doing a good job or not.
Okay. Thanks.
Now, following up on that, so you said you train your models. Is it trained against hardware specific information, or if you can say it?
Yeah, I cannot.
Fair.
Yeah,
So
that.
I don't know, on page 11, is this page 11? No, the one before it.
Sorry. So I say that again?
Page 11, sorry, if you can go to slide 11. Oh, maybe there is no.
Oh, yeah, it's a hidden slide actually.
Okay, maybe I just wrote it wrong then.
Was it 10
Yeah,
or
sorry,
12?
I had a question. No, I had a question about the queuing optimization, the slide 10, I guess.
Mhm.
In the queuing optimization here, are you considering multiple QPUs? So you have like you're thinking about I have a set of circuits. I might have cut those circuits among like in smaller circuits or whatever, and you want to schedule them. Do you have like do you consider multiple QPUs and then you decide where it should run?
So queuing optimization is something that we haven't fully implemented yet. It's like a work in progress thing, and we were more or less focused on throughput and performance characteristics in this. Yeah.
And then the next slide, in slide 12, I just wanted to clarify, I think I understand, but just to make sure, when you divide the subcircuits, you're actually saying that some of the subcircuits I'm going to actually simulate and not run on a real QPU.
Yeah.
And
Yeah.
you're combining simulators and real runs on real hardware. Did
Yes.
you find any problems because I guess the noise, there's different noise models for different, like the simulators can be noiseless, but then the hardware can be noisy.
Mhm.
How do you, like, you have something that deals with that sort of complexity?
Not on top of my mind particularly, but yeah, we'll have to check this report because we did circuit cutting couple years ago. And yeah, this is an example of that process entirely. So yeah, I'm not on top of my mind.
No problem, no problem. And sorry, one last question and then I'll be done. The token authentication, have you ever, did you guys look into that at all? Like when you integrated with Slurm and you need to generate a token to actually talk, because we're going through that right now with our system. You have a QPU, it needs a token to authenticate the API. Do you generate it manually and then set some environment variable and then you get your API to read it, or do you have some automated way of doing that?
So like in this one, yeah, we have like the authentication initially just happens when we are interacting with the QIO. So not until Slurm is coming into the picture, we are using that particular authentication key or something right now. But
Okay,
yeah,
that's
that's
manual.
an ideal. Yeah, what you are saying is an ideal scenario, like how the user authentication should be done. You send like multiple jobs, you have multiple users, you would have to keep their token somewhere safe, and then you will have to have it go through all the steps in the process, right?
Yeah.
So
But you don't have a solution for that, or you're still working on that area. You haven't
yeah,
gone
yeah,
towards
we
that. Okay.
haven't integrated it yet.
Okay, fair.
Yeah,
Thank you. I'm sorry for the barrage of questions.
absolutely. Welcome back.
Anybody
Peter
else has any
has a
questions?
question.
All right, cool. Thank you so much for your time and for the presentation. If you don't mind sending me the slides when you're ready, that'll be great.
Yeah, sure. Thank you so much for having me.
Thank you.
All right. Thank you.
Thanks for
Thank
the
you.
great presentation.
Yes.
Nice to
Thank
meet
Thank you.
Thank
Bye.
you.
Bye.